Hi, welcome back. Today I want to talk about logistic growth problems. Logistic growth problems are an excellent way to actually utilize differential equations in calculus, and they're one of the most applicable ways to use calculus in the real world. I think they're really, really fascinating. So before we begin with that, our logistic differential equation. The differential equation is in the form dp over dt equals kp times 1 minus p over L, where p is our population, K is our growth rate, growth or decay rate, and L is our limit. Okay? And if we integrate that, we actually get the solution, P equals L over 1 plus AE to the negative KT, where A is a constant. So I can actually show you what that differentiation looks like. So if we're asked to solve that, we have dp over dt equals kp, oh, and t is time, by the way. T is time. dp over dt equals, I wrote t is time up there, kp times 1 minus p over L. We can rewrite that as kp times L minus p over L. Right? K and L are constants. So we're going to solve this differential equation. We're going to move things to the same side. So we get dp over p times 1 minus p over L. Right? This part here is equal to the integral of k. I break up this integral here. I'm using separation or partial fractions, right? And I still have this. So I have ln of p minus ln of L minus p equals kt plus c. Take my natural, I can rewrite that natural log. So I get this. Then I ln both sides, and I get L minus p over p is e to the negative kt minus c. Then, remember our properties with e to something minus c, that c can come out and be a constant. Now I'm going to write that constant as a in this form with logistic growth, but it's still just a constant c. So now we have L minus p over p equals a e to the negative kt. And then if you do a little bit of mathing, you get this, rewrite this, we get p equals L over 1 plus a e to the negative kt. And we're going to use this formula and this formula when we're talking about logistic growth. So let's do a few problems here. The population of coyotes in a wildlife preserve is modeled by a logistic function. The preserve can support no more than 100 coyotes on the property. We already know by looking at this that L, if it can't support more than 100, that L is going to be, or our limit's going to be 100. So we're asked to write the differential equation with k equals 0.01, where t is measured in years. Well, that's easy. dp over dt is just going to be kp times L minus p, or kp, right? So dp over dt equals kp times, let's go back, check here, 1 minus p over L, right? 1 minus p over L. So we can write this as 0.01 p times 1, this should be a 1, even though it looks like an L there, minus p over 100, okay? So where would a horizontal asymptote for this appear on a graph? Well, if I had a graph at 100, I would have a horizontal asymptote because that wildlife preserve can't support more than 100 coyotes, right? And what would actually happen if that initial population is above the asymptote? Well, then the population of coyotes would start decreasing, meaning they would start dying actually because the preserve would be overpopulated. So if the preserve begins with 20 coyotes, we want to sketch a graph of that. Well, I've already done that. We start at 20 and we're going to grow up to about 100, right? That's our limit. Let's continue with this. We're asked to find the general solution and the particular solution of the differential equation such that p of 0 equals 20. Well, we have that equation that we wrote here. dp over dt equals 0.01 p times 100 minus p, right? Okay, so again, we have dp over dt equals 0.01 p times 100 minus p. We've already written that out. We can actually solve that differential equation, and you can see we could go through all of this work, and we end up getting p of t equals 100 over 1 plus a e to the negative t, right? So our k value there, 0.01, or actually in this, once we actually work through this, it's going to be, you can't see there, once we work through this, your k is not going to be the same for the differential equation and for the solution. Your k for the solution is like this k here, sorry, is equal to L times k. So our limit is 100 times 0.01 is 1, right? I hope so. 100 times 0.01. Yes, so 100, so in this case it was 100 times 0.01. That's going to be equal to the k in the solution. Okay, so we have that. And then we can use our initial situation. P of 0 equals 20, so we know P of 0 is 100 over 1 plus a e to the 0. Anything to the 0 power is 1. Do a little bit of math. We get our value for a. So we know that P of t, this is our general solution here, such like that P of 0, we can use this to find the population at any time, right? So we're asked, when will the coyote population reach 80? Well, we need to solve for t, so we're going to set 80 equal to our equation here. We do our math, calculate, we get t is the natural log of 16 years, which is about 2.77259 years. Now, we're also asked when is the coyote population growing the fastest? Well, that's going to happen. Any population is going to be growing or decaying the fastest when the limit is divided by 2. Okay, that's your point of inflection. So our population is, or the population growing the fastest when the limit is 2 divided by 2. So 100 divided by 2 when our population is 50. Now, you could actually calculate when that is by using our equation. I'm not going to do all the work, but basically t will equal about 1.35386 years. So it's growing the limit. Oh, no, I was actually asked to find the limit. Sorry, ignore this here. But find the limit as t approaches infinity of p of t. I don't need to calculate any of that. I was already given the limit. That limit is 100 because as t approaches infinity, as time approaches infinity, that game preserve still cannot support more than 100 coyotes. That's impossible. Okay? Let's do one more example to work through. And I want to do this with Newton's law of cooling. All right. So Newton's law of cooling is in the form dy over dt equals k times y minus b, where growth is when k is greater than 0 and decay is when k is less than 0. And our solution is actually y equals a e to the kt plus b, where a is going to be equal to y sub naught minus b, and y sub naught's our initial quantity. Okay, so a good tip is to factor out k before you start solving that differential equation. Let's actually do a fun problem here. You bought your favorite frozen coffee treat on the way to school at the drive-thru. Your car is always kept at a constant 65 degrees Fahrenheit. It took 10 minutes to get to school. The drink warmed to 35 degrees after 10 minutes. After another 10 minutes of getting your things from your locker and talking to your friends, the drink warmed to 50 degrees Fahrenheit. Use Newton's law of cooling to estimate the following. What was the frozen coffee's original temperature? Okay, let's find out. Well, dy over dt is going to be equal to k times y minus 65. That 65 is b, which is the temperature of the surrounding area, right? And that's the temperature here of your car, okay? So we solve that differential equation, and we end up getting y equals a e to the negative log over 2 of 10t plus 65, okay? It took 10 minutes to get to school, and the drink warmed to 35 degrees in that 10 minutes. So we know that 35 degrees, the temperature, T, is equal to AE to plus 65. We can actually solve for A. So A, our constant, is going to be negative 60. So now we want to know what was the coffee's original temperature. Well, I actually have more information here. After another 10 minutes of getting my things from my locker, the drink warmed to 50 degrees. So at y of 10, it was 35 degrees. At y of 20, it was 50 degrees. I can set these up. So I have 35 over 50 equals AE to the 10K plus 65 and AE to the 20K plus 65. Solve mathematically. I get K equals negative ln of 2 over 10, right? That's what I did to solve back over here to find my K. And then I got my A. So now I need to know, what was the original temperature? Well, that means I'm going to find, I have my Y here. I can find y of 0. My original temperature was 5 degrees Fahrenheit, right? It was a frozen coffee drink. It started cold and it got warmer throughout the day. Hopefully that made sense to you. Kind of look through these notes and see if they're helpful to you. I think it's really, really interesting doing logarithmic work, and definitely something that is a fun skill to have. So any questions, leave them in the comments, and I'll see you in class. Bye.